Okay, so if we think about it, chapter 5 should have been mostly review for you guys, okay, because it's all about 2 and 3 degree of freedom systems and how we find the equation of motion, the natural frequencies and the mode shapes, and then the general solution, okay. And chapter 6 we moved on from that by looking at modal analysis and how we can use that to solve problems where we have a forcing function being applied to that system, okay. And so this question is going to go through the process of finding the equation of motion, natural frequencies, mode shapes from chapter 5, and then we'll move into modal analysis to work out the exact solution for the particular problem. Okay, so that's what we're going to do. And the problem is a simple 2 degree of freedom system, okay, it's not that complicated. But the skills that we're going to go through are the ones you need to know. Okay, so we've got a 2 degree of freedom system. Okay, with 2 masses, and we've got m here, and we've got 3m here, 3m. Okay, and between them there's some springs, and these springs we have a constant of k here, 2k here, and 3k in this one. And we'll call this one x1, positive to the right hand side, x1, and we call this one x2. And there's going to be a force being applied to these masses. Well, in fact, one of the forces is in fact 0, but let's draw both to be consistent. And there are some constants associated with this. So we've got some values for k, m, and F1. So k is 150 newtons per meter. M, each mass is going to be m is 1.5 kilograms. F1 is 8t newtons, so that's a linearly increasing forcing function. As time goes up, the force being applied goes up, and F2 is 0. Okay, so there's no force being applied to F2. So the only force that's being applied is to the first mass, x1, or m1, okay, which has a mass of 1.5 kilograms. And that force is going to slowly increase with time, okay? And we want to find out what is the response of the system. So we have to go through the process. So this part is sort of revision of chapter 5. Okay, revision of chapter 5. And the first step is to find the equation of motion. Okay, so we can use the quick method. And the quick method states that for a linear system, the mass matrix is simply the masses down the diagonal. So we've got m and 3m, 0 and 0. Okay, so there's the mass matrix. And that is multiplied by the acceleration of x1 double dot, so x1 and x2 double dot. So there's our MA, Newton's second law. And then we have plus, there's no damping in this situation, so we can go straight to the stiffness. And the quick method states that the diagonals of the stiffness matrix are the stiffnesses connecting each mass to ground or to another mass. Okay, so for the first mass, we can see that we've got k plus 2k, so that's going to be 3k here. Sorry, I apologise, this is in fact k. That's a mistake. This is just k, it's not 3k. Okay, so we've got 3k for this one. For the second mass, we've got 2k plus k, so this is also 3k. And for the off diagonals, which are these points here, 1, 2 and 2, 1, you look at mass 2 and mass 1, and you look at the springs between the two, okay, and it's going to be minus the sum of those springs. So in this case, we have simply minus 2k between mass 1 and mass 2, and minus 2k, which is between mass 2 and mass 1. Okay, so it's a symmetrical matrix over the diagonal. And that is multiplied by our displacements. So we have x1 and x2. And that equals the applied forces. So we have F1 and F2. So there's the equation of motion in terms of variables. And since we've been given some values for m and k and F1 and F2, we can rewrite this with the actual values in. So I'm just going to rewrite this with our value of m being 1.5. So this is 1.5, 0, 0, and then 4.5 because it's 3m. Times by the acceleration, x1 double dot, x2 double dot, plus, and then we've got 3k, well k is 150, so that's going to be 450, minus 2k, so that's minus 300, we have a minus 300 here, and then 3k again, so that's 450 down here. Times by the displacements, equals, we have 8t here, and we have 0 here. There is our equation of motion. Tick. Okay, so the next step is to find the natural frequencies. Now to do that we make a substitution, okay? We say that xi equals xi cosine of omega t, big Xi cosine omega t, okay, because it's going to oscillate. Or equally, we could make the substitution that that's going to be the real part of xi e j omega t. Because if you remember way back in chapter 2, we discussed how the real part of a complex number or a complex exponential is cosine of omega t, okay? So either of those substitutions work, because if you take the second derivative of either of those, okay, we're going to get big Xi times by minus omega squared cosine omega t. And you could do the same thing here. We get the real part of big Xi minus omega squared e to the j omega t. So they result in the same thing. And so we can substitute those back into this equation. And we can rearrange it, and we end up with the mechanical impedance matrix. So I'm going to put this back into this equation. We're going to with 450 minus 1.5 omega squared minus 300, and then we've got 450 minus 4.5 omega squared. x1, x2. Now, because the natural frequency is unaffected by the force being applied, we set the force in this bit to be 0, because that's how it's going to help us solve the problem. Let's move it up. Now to find some values for omega 1 and omega 2, we have to find the determinant of this mechanical impedance matrix, which I'll call that KD. Okay. And so that's going to be 450 minus 1.5 omega squared times by 450 minus 4.5 omega squared minus 300 minus 300 equals 0. So the determinant of the 2 by 2 matrix is these two terms multiplied together minus these two terms multiplied together. Okay. So 450 times by 450, 2002, well no, let's see, hold on. 202,500, okay. Using the calculator, okay. 1.5 times by 4.5, sorry, let's go for 1.5 times by 450, so we have minus 675 omega squared. 4.5 times by 450, we have minus 2025 omega squared. And then 1.5 times by 4.5 is 6.75, so plus 6.75 omega to the power of 4. And then minus 300 times by minus 300 is 90,000. Okay, but it's a minus 90,000, so we have minus here. 90000 equals 0. So that's some simple arithmetic multiplying quantities out. And then we can group some of these things together because some of them make sense. So let's put this omega to the power 4 at the front. 6.75 omega to the power 4. Then we've got the omega squared term, so we've got minus 675 minus 2025. So that's going to be minus 2,700 omega squared. And then the omega to the power of 0, we've got this term and this term. So that's going to be plus 112,500 equals 0. We have a quadratic equation, okay, in terms of omega squared. So with a quadratic equation, we can use the quadratic formula. So omega 1 and 2 squared equals, well, we have minus b, so that's 2,700, plus or minus the square root of b squared, which I happen to work out as being 729, so 7,290,000, minus 4 times by a, which is 6.75, times by c, which is 112,500. Divided by 2 times a. These numbers look scary, but obviously you have a calculator in the exam, so you shouldn't be posing you any problems. You could divide all these numbers by 6.75 to make a equals 1, and those numbers would obviously be somewhat smaller, but it's up to you how you do it. You should result in the same solution either which way. And so this equals 2,700 plus or minus the square root. I've done the sums for you. We've got 4, 2525, 25, 25, 0, 0, divided by, obviously this is 13.5. So we plug in the numbers into the calculator and we get two values. We get 352.7525, or we get 47.2475. So we're going to set omega 1 squared to be the first term, 352.7525, and omega 2 to be 47.2475. Now it doesn't matter in your solution whether you've chosen omega 1 to be the second number or the first number. Okay? Either will be perfectly valid. Okay? And obviously if you take the square root of these, we'll get the omega 1 in terms of radians per second. So omega 1 is 18.7817. And omega 2 is 6.8737. 8737. Okay. Step 2, natural frequencies. Now for the mode shapes, we have to go back to our KD, our mechanical impedance matrix, and plug in our values for omega 1 and omega 2 and solve for that mode shape. Okay? So let's write the mechanical impedance matrix out. So there's the mechanical impedance matrix. And then in the brackets, in this vector, I've divided both sides by x1. So the top one will be 1, and the bottom one is x2 over x1. Okay, and I'm going to call that R. And so that means that this here will be my mode shape. 1 R. That's my R. I'll call that mode shape S, whatever, or I. It's up to me. Okay. And so to find R1, we have to plug in omega 1, and to find R2, we have to plug in omega 2. Okay. But what I'm going to do before I do that, I shall set up an equation that allows me to solve R. So I do this number multiplied by this number, and this number multiplied by this number equals 0. So we could write that equation out for 50 minus 1.5 omega squared minus 300 R equals 0. Therefore R equals 450 minus 1.5 omega squared divided by 300. So to find R1, we have 450 minus 1.5 times by omega 1 squared, which we have up here as 352.7525 divided by 300. Do the sums, and you get minus 0.2638. Therefore, x1, which is our first mode shape, is 1 minus 0.2638. And R2, it's the same equation, 47.2475 divided by So those are our two mode shapes. In the first mode, if x1 moves up by 1, then x2 will move down by 0.2638. And in the second mode, in the second natural frequency, if x1 moves up by 1, x2 will move up by 1.2638. Okay, so those are two mode shapes. In one sense, they're vibrating in opposite directions, and in the other sense, they're vibrating in the same direction. Now from this we could then find the general solution. We've got the equation in the book, we've got the natural frequencies, we've got the mode shapes. You could find the general solution where you'd have to find C1 and C2 using initial conditions, and you'll have a solution. Okay, but we're not going to do that. We've got that's for free vibration. Here we've got some forced vibration, so we're going to extend that onto the stuff in chapter 6, which is on modal analysis. So that stuff is from chapter 5. We're now going to use that data for the modal analysis section, which is review of chapter 6. So revision of chapter 6. Okay, so chapter 6 covered a technique called modal analysis that allows you to go through and solve the problem. You go through a number of steps. The first few steps we've already done, because that's the stuff from chapter 5. Okay, a number of steps that allows you to get to a solution for x1 and x2 for such a system where you've got a force being applied. Okay, and so let's go through those steps. Step 4 is where we find these things called the modal masses. Okay, and those values of modal mass allow us to rescale the mode shapes to some. They're still the mode shape, but they are rescaled, and that will then form what's known as the modal matrix. Then we use the modal matrix, which is this key, to unlock, to uncouple the equations of motion. You end up with two uncoupled equations of motion, or two uncoupled modal equations, which are second-order differential equations that are easy to solve. We did that in chapter 3. And the solutions to those differential equations are in your equation sheet or the formula sheet. So you don't need to go through solving them. Okay, any questions that I may give you will have the solution on the equation sheet. Okay, you then apply that solution to these second-order differential equations, and then once you've done that, you then reapply the key, the modal matrix, to go back to your solution x1 and x2. And so let's do that. Step 4 is modal masses. And the equation for modal masses was you take your mode shape, x1, or xr, I'll call it, or xs even, whatever. You transpose it, you multiply that by the mass matrix, xr. Okay, so that's the equation. And so for the first mode, r will be 1. And so we can write this out. So M1, so that's the first mode, which we've got up here, but it's been transposed, so we have it written out like this, times by our mass matrix. This is 1.5, 0, 0, and 4.5. And then we write the mode shape as it's written up there, minus 0.26338. Now when you've got these three, well, the two vectors and the matrix to multiply together, it's much easier to multiply these last two together first, together vector, and then you have one vector multiplied by, well, row vector multiplied by column vector, which is possible, and you can get a value for that. So to do these two first, we obviously it's 1.5 times 1 plus 0 times minus 0.2638, and it's 0 times 1, and then 4.5 times minus 0.2638. So let's rewrite out this first one. 1 minus 0.2638. And then we have a column vector of 1.5. And then 4.5 times by this value gives us minus 1.1871. Those two we can multiply together relatively straightforward. It's 1.5 times by 1 plus minus 0.2638 times by minus 1.18171. So I'll write that out in full. We have 1 times by 1.5 plus minus 0.2638 times by minus 1.1871. And if you do the sums, that comes out to be 1.8132 as M1. So M2, we follow exactly the same process. 1.2638, 1.5, 0, 0, 4.5, 1.2638. Again, you multiply the last two things together first. So those are our two modal masses, M1 and M2. Okay, so that's step 4, which is working out the modal masses. The next step is we need to rescale the mode shapes. This allows us to have a 1 in front of the second derivative in the modal equations, okay, which helps in terms of our analysis. And to rescale the mode shapes, we set up two mode shapes, U, okay, U1 and U2, I'll call it UR in this case, and we take the mode shape that we have, x1 and x2, and we divide it by the square root of our modal masses, M1 and M2. So that's mode shape R. We divide it by the square root of MR, and we get a new mode shape, UR. Okay, and then those two mode shapes lined up next to each other will form our modal matrix, which, like I said, is this key to unlock or to uncouple the equations of motion, the coupled equations of motion. And so we can write U1. We take our x1, which is 1 minus 0.2638, and we divide both of those terms by the square root of our modal mass, which is 1.8132. So you do 1 divided by the square root of 1.8132, and you do minus 0.2638 divided by the square root of 0.8132. And so U1 becomes 0.7426 and minus 0.1959. So we can apply the same equation to U2, and we get another mode shape, 0.3393 and 0.4288. So these mode shapes are exactly the same as these mode shapes. If you look at the relative displacements, they are exactly the same. If you took one divided by the other, you get the same value as if you did one divided by, this divided by this will be the same as this divided by this. It's exactly the same. They've just been rescaled slightly, okay? And they've been rescaled to ease this process. So they're perfectly valid mode shapes, but they've been rescaled. And so from these two mode shapes we can work out what phi is. It is basically U1 and U2 next to each other. So we have the four values in this matrix, 2, 6, minus 0.1959, 0.3393, and 0.4288. Now the reason we've done this rescaling, just as an aside I guess, we have our equation of motion, which is m x double dot plus k x equals our forces, so I'll call that f t, because it's a function of time. That's the equation, okay, and then we apply the substitution where we say that x is going to be our phi times by our modal coordinate q. Okay, so if you apply that substitution into this equation, we end up with, obviously, x double dot. This is just a constant, so you multiply it by the same constant, and you get q double dot. So we put these substitutions in here. We have m phi q double dot plus k phi q equals f t. And then what we do is we pre-multiply both sides of the equation by the transpose of phi. So that's why I've left these gaps. In front of this we put phi t. So phi t. And obviously I've got to do that on this side as well, phi t. And why we do this is why we've rescaled, because this term simply gives us the identity matrix. And this term gives us omega 1 squared and omega 2 squared, 0, and 0. So you end up with an equation where you've got 1 times by q double dot, and then omega 1 squared times by q1, and omega 2 squared times by q2, okay, equals the forcing function that's been applied by the transpose of the, that's been multiplied by the transpose of that modal matrix. Okay, and you end up with a nice equation that's very easy to solve. So let's do that. We need to work out what these forces are, so that's the next step. Deal with applied forces. If I've gone so fast that you've missed something that I've written, then please let me know, and I'll be able to tell you. And I'm also sorry that the contrast at this end of the screen is worse than that end of the screen. It makes the stuff down here harder to read. So to deal with the applied forces, we take this term and we work it out. We take the transpose of phi, so I've called them F1 and F2, but little f1 and little f2. And then here I've got my applied forcing function, and this is the transpose of the modal matrix. Notice that the transpose, the diagonals remain the same, but all the off diagonals swap places. Okay, so that one and that value have swapped compared to this one. That's the transpose. And so we can multiply this out. This is obviously those two numbers multiply together plus those two numbers multiplied together. Well, that's 0, so it's just that times that. And then the same down here, we've got those two plus those two. So again, it's just that times that. So it's going to end up with a vector, and we have some values. We have 5.9411 times by t, and we have 2.7142 times by t. So although the second mass did have no force being applied to it, the second modal coordinate will have a force being applied to it. So there's our applied forces. We then can write out the modal equations. So that's basically these equations that we can write out, knowing that, this equation being written out, knowing that this term is going to be 1, because it's the identity matrix, and this term is going to be omega squared. And then obviously we've just worked out what those terms are going to be. So we can write out the general form, which is qi plus omega I squared times by qi equals fi t. Okay, there's the general form. That they will always, if you've rescaled those mode shapes, you will always end up with an equation in this form. Okay, no matter how complicated the question is, those equations will always be in that form. And so we can write out for I equals 1, we have q1 double dot plus omega 1 squared q1 equals 5.9411 times by t. And we found omega 1 and omega 2 earlier on, so that's why I've just written it as omega 1. So that's for I equals 1. And for I equals 2, we have q2 double dot plus omega 2 squared q2 equals 2.7142 times by t. Now, what next? Well, we solved in chapter 3 the equation mx double dot plus kx equals ft. Back in chapter 3 we solved that equation. And on your formula sheet, which you have the solution to that equation in the general form. Okay, and the solution to that equation was x of t, for initial rush conditions this was, not the general form, is minus f divided by k omega naught sine of omega naught times by t plus ft divided by k. So that is the solution to this equation. That's the solution to this equation. What you need to do is you need to match this equation up with this one. So if we write that equation out, mx double dot plus kx equals f of t, and here we've got qi double dot plus omega I squared q equals, I'll call this, I don't know, they could be called ct, okay, where c1 is 5.9411 and c2 is 2.7142. Okay, so I've just called that C. And we can match them up. We can see that M equals 1, K equals omega 1 I squared, okay, F equals C. And in this equation, omega naught squared will equal omega I squared. And so we can plug these numbers into this equation. So for qt, we've got minus, obviously c1, which is 5.9411, divided by k, which is omega 1 squared, and we've got omega naught, which is going to be omega 1. So we have omega 1 cubed. Omega 1 cubed, we can work it out. Well, omega 1 we've got is 18.7817 cubed times by sine 18.7817 times by t plus 5.9411 times by t divided by k, which is omega squared. So we have 18.7817 squared. There's our solution for Q1. And Q2 can be exactly the same process. We have minus 2.7142 divided by omega cubed. So that's 6.8737 cubed times by the sine 6.8737 times by t plus 2.7142 divided by 6.8737 squared. So that's Q2. Thank you. So there's a T at the end of this equation. So that gives us Q as a function of time. Then to get X as a function of time, we apply the key again. We apply this equation. Well, we've now got Q, we've got the matrix, you can therefore find X, okay? So, yes?
Why is it cubed and we put the denominators there?
Why is it cubed? Because we have, on the bottom of the solution, we have a K and we have an omega 1. Okay, now when we match up the equation, we can see that K equals omega 1 squared. And so you have omega 1 squared times by omega 1 gives you omega 1 cubed. Okay. I'm not going to write this out in full, and nor do I expect you to do so. So you can simply write, if you wanted to, x1t equals 0.7426 times by q1 plus 0.3393 times by q2, and x2t is minus 0.1959 times by q1 plus 0.4288 times by q2. Have people finished with this top page? Yeah? I'll do that. Okay, so that's a revision for chapter 5 and chapter 6. Now obviously, if the forcing function on that wasn't a linear forcing function, it was, say, a sinusoid or a rectangular step forcing function, or even an exponential, decaying exponential, you would therefore have to apply the equation on the formula sheet that's a solution to those problems. Okay? So for the exponential, we had a solution, and for the rectangular forcing function, we also had another solution, and you simply apply that equation to that problem.